In the last part here, let me consider what our universe is doing and what is the fate of our universe. And this will be a no dark energy consideration. Well, Edwin Hubble established that the galaxies are flying away from each other. So all the galaxies are receding from each other. But the gravity of the galaxies tug on each other to slow down that expansion. It's all very understandable. So it seems like the possible outcomes would come down to just two basic ones. Namely, if gravity is strong enough, the expansion will halt and then reverse into what's known as a big crunch. It's just like throwing a ball high up in the air. If you don't throw it fast enough, it will come back down, crash back into the earth, or land back in your hand. The other possibility is that if you throw that ball really, really fast, it can escape the gravitational clutches of Earth altogether and never return. If the expansion is rapid enough, then the galaxies, the universe, continues to expand, and it never ends. It expands forever. Now, if it's just a matter of gravity tugging back on itself, as traditionally thought, then the universe only needs about 10 to the negative 29 grams per cubic centimeter to halt and recollapse on the average. That's just a couple hydrogen atoms per cubic meter. This is known as the critical density of mass, matter density in the universe, to halt the collapse and bring it back onto itself, or to hover between those two considerations. So is the universe expanding fast enough to escape its own gravitational pull? Keep the thing expanding forever? That's what's going on? Well, it's just a little bit more complicated than this simple picture. And let's consider a couple other concerns. One of the complicating factors is that mass and energy bend space. So we have an overall geometry of the space of the universe. And they can fall into one of three categories. That determines what the shape of the universe is. And it depends on the density. The geometry will follow from the density. We can construct triangles on the shape of the space-time associated with these different geometries, and it produces lines at different angles. For instance, we're used to flat geometry being like in Euclidean space, where the angles of a triangle add up to be 180 degrees. But we have what's called open geometry, where if we construct a triangle, it'll be less than 180 degrees when we add the three angles up. Or spherical or closed geometry. If we make a triangle on a sphere, for instance, some of the angles will exceed 180 degrees. The symbol omega naught in particular, is the density of the universe compared with the critical density, where there's just enough matter and energy to produce a universe that just halts its expansion. That's what it's concerned with. This would correspond to a flat universe. If it has less than that density, it's open geometry, or more than that density, greater than 1, omega naught greater than 1, it's spherical or closed geometry. So those are the three possibilities. Now the curvature of the universe can vary in space because of the supercluster distribution and all, but on the whole, the universe has an overall shape. Now, as we measure characteristics of our universe, we measure it to be close to critical density, which basically says that we live in a flat universe. The critical density is about equal to 1. So, geometrically, we have a flat universe. Now, we do have evidence for the geometry of the universe, and it comes, surprisingly enough, from the cosmic microwave background radiation. So the small irregularities in the temperature at different angular scales reveals the curvature of space and thus the geometry of the universe. And the way it goes is that if the universe is closed, then light is bent from a hot spot in the background radiation toward itself. Two parallel beams of light in that kind of universe would converge. And so how we perceive those hot spots is at a greater angular displacement than what they actually are. So they appear larger. If the universe is flat, then the light from opposite ends of the hotspot are not bent, and we see them as their true size. If the universe is open, meaning the critical density is less than critical, then in the same way that two parallel beams of light would diverge from each other, these light from opposite ends of the hotspot would be diverging. So the way we would perceive it is being smaller than it actually is. Well, as we take the measurements, it turns out that the temperature variations are about 1 degree, and that's consistent with the theoretical understanding of the dimensions of these hotspots, which is consistent with a flat geometry, not a closed or open geometry. So that is the best information and evidence we have for the actual geometry of the universe. So what is our universe really doing? What is the situation in our universe? The mass of the stars is only about 0.5% the critical mass needed to halt the expansion. So in order to be consistent with the flat universe, having the critical density, dark matter would have to be 200 times this much to do the job. Unfortunately, from what we've already discussed in galaxy and cluster studies, the dark matter is only about 25% of what's needed to produce this critical density. Now, white dwarf supernovae are used to test whether the expansion has been slowing down or what it's been doing. And very surprisingly, in recent times, the evidence points to the fact that the universe is actually speeding up instead of slowing down. So this is going to lead to what is known as this mysterious dark energy. But the 4 basic expansion patterns can be summarized here. And let's see if we can figure this out. As you look at the 4 basic models, the thing to notice is that here is the present time slicing across all the models. This is future time, and this is past time. All of the models have to be consistent with what we see now. The present state of the universe is the same in every one of these models, as it must be. But how did it get to this point? And then what are the implications for the future? What will happen after the fact? The first 3 assume only gravity slows the expansion, and that makes a pretty big difference. So in the first one, the matter density is greater than critical. Gravity will halt the expansion here and then reverse it and bring it to a big crunch in the future. That's a recollapsing universe or a closed universe. In the second one, the critical universe, matter density is just critical. So you have this expansion, and it never quite stops in the expansion, but in infinite time would actually come to a stop. It never have enough stuff to contain within to reverse the expansion. And the third one, matters the density is less than critical, and the expansion continues relatively unimpeded, known as a coasting universe. And then on the fourth one, we have this mysterious dark energy producing a repulsive force, causing the universe to accelerate with time. It looks quite a bit different, doesn't it? The galaxies then obtain larger and larger redshifts with time. As you go through time, the galaxies are increasingly redshifting, and the universe becomes cold and dark much more quickly than they would in any other model. This also has implications for the age of the universe. As you can see in these 4 models, notice that the origination point is progressively deeper back in cosmic time. So the more matter density a model has, the less time there needs to be from when it began, because the rate of slowdown is greater for a greater density model, in brief. So the initial rate of expansion diminishes for each model, requiring more time to arrive at the present size. And this 4th model requires the most time to arrive at the present size. And that actually appears to be the state of our actual universe. A universe that is significantly modified by the presence of this mysterious force known as dark energy. Now, is there evidence for acceleration? Actually, there is. And this graph could get a little confusing, but I'm going to try not to let it. We have four basic models here: a recollapsing, critical, coasting, and accelerating, all of which have different characteristics. And right now, everything has to be consistent and have the same characteristics right now. This is the present time, this is future, this is past. So you notice that the directions the graphs are going in all four models is the same in the current epoch. Now there's white dwarf supernova that you're familiar with, and when we plot their distance on a graph, and this is time, they manifest characteristics that show that they're actually too dim. They're dimmer than they're supposed to be. And that has implications for the model. So I'm not going to try and describe that in any detail. But a rising curve means the universe is expanding. A falling curve, which is only one, this here, falling, means the universe is contracting. So only in this recollapsing universe do we have the universe reducing in size at any point. Collapsing universe is also known as closed, meaning the geometry of space-time is sufficient that it wraps itself into a spherical type of shape. Now, as I said, the white dwarf supernova are too dim for their redshifts, and thus basically what that means is they're too far away. They're farther away than they should be. Okay, so let's just take that as a given. So as such, they reveal an accelerating universe, since they had to travel further in the longer epochs of time in the early universe. So they had a lot of time was needed to travel to this longer distance. They're further away than they reveal themselves to be based on their redshift. So putting all that together, and the fact that the model has to be consistent with other age indicators, this is the best model for our current universe. A key consideration is that it reveals itself to be about 14 billion years old, which it must be. The other models do not have enough time to evolve to the present condition to be consistent with the age of the universe as determined by other measures such as globular cluster ages and radioactive studies. So we live in an accelerating universe that's significantly modified by this thing known as dark energy. Now, we've discussed that the geometry of the universe is measured to be flat. And just keep in mind that this flat geometry is a little more complex than we generally think about. We're talking about four-dimensional space-time that's flat. And that's actually very peculiar, because it's very unlikely that it would be just exactly flat. That would be at that critical density with the stuff contained in the universe. Because any original deviations that would distinguish it from that perfection would magnify themselves as time goes on. So the initial conditions of the universe have to be very carefully chosen in order for this to be the case in the present day. As you see this region here, notice that the curves look very much in line with each other right here, magnified. There's not much deviation in the way that the evolution of the universe is going here, but later on the differences are highly magnified, kind of like a trick pool player. The initial condition of what he does with the first hit of the ball is going to have serious implications for about 3 or 4 or 5 bounces in progression. So why would it be so close to that critical density? That's the question. It would have to be near or exactly on that critical density to a precision of at least 1 part in 10 to the 50. That's a tremendous amount of fine-tuning, so to speak, that's required for that to be the case, so that it measures to be flat in our current epoch of time. So that 13.7 billion years in the future, the universe still measures to be flat. It's like balancing 1,000 pencils on sharpened tips on a hard table simultaneously. Now that just sounds insane, but 1 part in 10 to the 50 is consistent with that kind of insanity. Our universe hangs precariously on being flat, closed, or open right from the beginning. Notice these densities here. All these digits are the same except the last decimal place here, grams per cubic centimeter, color-coded. So just this tiny deviation after all these digits can mean the difference between significantly different models of the universe in the current epoch of time. Vastly different with tiny deviations in the beginning. So you can see that this is something that really is a head scratcher, why it would be so perfect from the very beginning to be flat in our current epoch. So how does inflation address this problem? Well, the curvature of space is forced toward flatness. Zero curvature, so tremendously fast that it's flat even at this era of time, 13.7 billion years later. General relativity explains the effects of inflation on space-time. It's like the flattening of the surface of a balloon when you rapidly inflate it. Here's an ant in his own little bubble universe, balloon universe, and as you inflate that balloon, this observer, as his universe is inflated, notices less and less curvature. So from the point of view of his local region, he can't detect any curvature in the geometry of his universe. And the estimates of the amount of inflation are as high as a factor of 10 to 100. So you have this rapid stretching out, kind of like zooming in on an edge here. As you zoom in real rapidly, you notice the flattening as you zoom in. So that's how it can be thought of. The flattening would be so incredibly large that any curvature that the universe might have previously had would only be at scales much larger than the universe itself. So on the scales that we can observe, it would all be so flattened out to be able to detect no deviation from perfect flatness. So that's the answer to the flatness problem. Inflation, once again, comes to the rescue. So what is this mysterious thing called dark energy? This is more mysterious than dark matter. We don't know what dark matter is. Dark energy, there's nothing particularly dark about it other than we are in the dark as to what it is. In that sense, it matches our lack of understanding about dark matter as well. The reality is that we can measure the effects of a cosmic repulsive force that's actually accelerating the universe. And it's also the same mysterious entity that's increasing the overall density of the universe by adding energy, according to E is equal to mc squared, to produce the critical density so that we have the total matter energy density to make the universe flat, to produce that critical density. There's basically two possibilities postulated for this dark energy. One is known as the cosmological constant, and Einstein's equations allow for it, as we referred to before. In fact, he threw it into his equations. It acts as a cosmic repulsive force, kind of an anti-gravity force, to enable the universe to push against the effects of gravity. It's got this symbol here for the cosmological constant. And it's really energy from the vacuum of space itself, which seems really strange, but it's pretty well understood that the laws of nature have that reality associated with virtual particle pair production in the vacuum of space. That is a phenomena that can actually be measured. So it's not just an ad hoc assertion. So as the universe expands, there's a decrease in the density of the matter and energy. Space expands. It expands the material along with it. Material that's trying to slow down the expansion. But the energy density from the cosmological constant is, well, constant. That's why it's called the cosmological constant, not the cosmological variable or dynamically changing entity. So it's unchanged during the expansion. And at some point, that outward force exceeds the inward pull of gravity, and we have acceleration, just as is observed. The other possibility is quintessence, very similar, except that the energy density of space does not have to be constant. Now, there's less fine-tuning in the initial conditions to make the universe flat, so that it still measures to be flat now. So with quintessence, we can have the value of the energy density of space modified with the expansion of space and also the flow of matter and energy throughout the universe. But in any case, whatever particular form it turns out to be, and the cosmological constant reveals itself to be the best model based on the evidence that we have now, matches the data best. This dark energy is spread out through all of space, and in fact, it's known as dark energy. So dark energy has the two possibilities, cosmological constant or quintessence. And the supernova data, the galaxies, show the universe went from deceleration to acceleration when the universe was about 6 billion years old. So for the last 8 billion years or so, it has been under a state of acceleration, about 40% of its current age. That's the state of affairs as we see them, and we are in the dark significantly about this vast majority of the universe that we just don't know about. So for all we don't know about the universe, the thing we are pretty confident about now, based on the data, is the universe will expand forever. So that is our ultimate fate. But what do we know about what the universe is made out of? Well, the stuff we are familiar with is just a tiny fraction of the whole. The most mysterious thing, dark energy, constitutes most of the universe, over 72%. The dark matter, over 23%. The rest of the sliver, the 4.6%, is the regular matter that we're familiar with. Now, of that 4.6%, really the normal matter is only 4.5%. The rest is, which is just a small amount, is the neutrinos, about 0.1%, and photons themselves, which is about 0.05%. And even this normal matter, the 4.5%, it's only a small fraction of this that we can actually visibly see because it's producing electromagnetic radiation that is visible from Earth. So we don't know what the vast majority, over 90% of the universe, is made of. It's kind of a sad testimony for cosmology. The exciting thing is that we're learning things at a rapid rate. My own prediction is that we'll understand what the dark matter is, I'll say by 2020. Dark energy, who knows? It may turn out to be something extremely surprising. Well, in all these circumstances, surprises are in order, so we'll just have to wait and see. And finally, the same visual I started this chapter on modern cosmology with, which is a wonderful portrayal of the evolution of our universe. Starting with quantum fluctuations and inflation, you see this inflationary period, and 380,000 years, finding the first radiation of the Big Bang itself, the afterglow, followed by the Dark Ages, and then the era of galaxies, development of solar systems, planets, right up to the present time. And here we have a whole expanse of 13.7 billion years. As recorded by WMAP, this background radiation has revealed many of these characteristics to us, including, as shown on this graphic, the slowdown of the universe. You see this curvature that's curved like this, and there's an inflection point somewhere around here, and this starts curving up as the cosmological constant, or in any case dark energy, takes over the slowdown as a result of gravity and causes the universe to accelerate. So it's our best picture that shows the reality of our universe. And hopefully at this point, after going through all this information, you have a much better feel for the true nature, as we understand it, of our amazing universe.